Okay, so our project was to detect lanes in dashcam images, and my partner on this project was Joel. So to introduce the project, this was actually based off of a research project done by Miffy Sevilla in 2017. Her project was to detect lanes from dashcam footage using a bird's eye view perspective conversion. She filtered out the background of the road and only kept the lanes in by using color and edge detection. And then she separated each line marker and fit them onto a curve, and then projected that curve back onto the original image as a polygon. So as you can see in the bottom there, there's a highlight of the lane that the car is in green.
So for data collection, as we tried to replicate this research project, we used my phone, a Pixel 2 XL, mounted in my car on just a simple magnetic mount. And we tried to capture a good variety of roads. You can see in some of these pictures, we got everything from curved on-ramps to intersections to highways. We ended up finding that particularly the lighting conditions and shadows had a significant effect on our results. So for the purposes of this project, we limited our scope to pretty ideal conditions. Another thing we ran into was with this magnetic dash mount, the phone wasn't terribly stable. So you'll see in some of the videos, the phone shakes a bit, and also we had to account for different angles of positioning for each time I put my phone up there. So these are all things that we had to factor in that we would maybe improve for next time.
So the first step to doing all this was to calibrate the camera. Because our source video was taken from a video and not direct photos, I had Joel take a video of this checkerboard pattern, print it out on a piece of paper, and record it from a whole bunch of different angles. And then we extracted a few frames from that and put it into MATLAB's built-in camera calibration. It rejected a few of the frames for being too blurry, but overall you can see it detected the points pretty well. And then on the next slide here, you can see that's our results from doing that. On the right, there's a good view of the checkerboard pattern compared to where the camera is located. So you can see we got a good range of all angles and all places within the actual frame of the video. So our mean error for that was 0.39 pixels, and a good target for that is about 1 pixel. So we did quite a bit better than we had to. There were some outliers and some frames that got rejected, like I said, but on the right there, you can see in that red box, you can drag to select your outliers. So I deleted all the ones that stuck out above the common result. So to transform these source images, we had to use a bird's eye transformation function built into MATLAB. And that gave us a top-down view of the original image. It transformed it from that first-person dash cam to sort of like a Google Maps type of view. We had to tune the camera height off the ground as well as the tilt. We had a little bit of yaw and a little bit of pitch on our camera mount. And like Joel said, that changed a little bit depending on how the camera was mounted. So if you would take it off to pause the recording and then put it back on, the angle was slightly changed, which caused a little bit of issue, but we can manually filter that out. And then as the lane markers got further away from the camera in the source image, they got blurrier on the bird's eye view of the image. And that's just because the lane markers would be further away from the camera itself, which is at a lower resolution, and they take up less screen real estate. So to split up the lanes, we did a little bit differently than the source research. We just split the image straight in half, and that allowed us to treat each image as its own separate entity, which allowed us for different filtering on the left half versus the right half, as well as the fit lines could be treated totally separately. Meanwhile, the original research did it a little bit differently. She used HSL image or color formatting, which is not officially supported in MATLAB. That's hue, saturation, and lightness rather than a red, green, and blue channel, as you can see in the bottom there. We tried to use a third-party function to convert our RGB images to HSL, but they were unsuccessful. They didn't work quite the way we expected to, and because it wasn't officially supported, we kind of dropped that whole idea. So the way she originally did it was for the white lane markers, white is independent of hue. So any color where the lightness was very high, regardless of hue or saturation, she filtered that out for the white lane. And then for yellow lane, she looked at purely like the yellow, the orangish to green sort of hue with high saturation, so that it was purely the bright yellow that you see on normal road paving. She then took the gradient of the lightness channel and then did a Sobel operator on it to find the vertical component of the image. And that filtered out even more of the background noise for the cases where the background was a little bit closer to the color of the road markings than usual. So she ended up with a really clean image. As you can see here, this is the line fitting that she did. Rather than splitting up the image like we did, she looked at the histogram of the pixel position of the two lane markers, and where those peaks occurred is roughly where the lane starts. So she split up the image into these little boxes, and the average X value within that box is how she knew where to place the next box. And so she just repeated that process of basically stacking these boxes on top of each other until there was no more room for these boxes. And then using the center point of each of these bounding boxes, that's how she drew her fit line. So it sort of split it up into multiple chunks rather than treating the entire image as one line to be fit.
So how we ended up doing our edge detection was we went ahead and just took our color image, which was RGB, and squashed it to grayscale. So we just set aside color, and we then applied a median filter to get rid of some of the noise we saw, and that cleaned it up enough to do a binary threshold. And we were able to tune that value that threshold value based on the lighting conditions for a particular drive. And then we took those binary images and did a linear fit to find the lines representing the lines on the road. So here's a look at the process for the left line. We ended up padding the image with zeros to keep it the same size for the left and right portions as the original image was, so that our linear fit equations would be all relative to the same 0 point. So we take the input in grayscale. This particular one didn't have too much noise, but for other ones, the median filter made a big difference. And then when we take that binary image, it's essentially, we essentially just treat it as like a scatter plot. And then we do a linear fit the way you would with any other kind of scatter plot data. And you might not be able to read it, but we solve the equation there for X given Y, since it's essentially vertical function. And we do the same thing on the right side. We then take these two equations and bring them back into the unified bird's eye view. And we evaluate these polynomials at both the top and the bottom of the image for both the left and the right. And that ends up getting us these 4 points that we have highlighted in red. So we then use the MATLAB function called patch to draw a polygon over the top of our original image to highlight where we're supposed to be driving. And if we go to the next slide, here you can see in a video us driving along. It's the original video on the left, and we're dynamically doing all of the filtering and linear fits on the right, and drawing the highlighted region for the lanes. You may notice there's some vibration and instability in the footage itself on the left, which does show up on the right as well. But you can see that our solution actually follows that very tightly. Ended up doing a really good job following that camera movement.
I guess I'd also like to highlight towards the end of the video here, it's coming up right now, the lane switches to like a double lane in the middle. And our algorithm was able to track that regardless of the fact that it switched from dashed to like a sort of like half dashed, half solid. So we thought that was pretty interesting as well. So if we had more time to do this, or we had a little bit more experience with the software, we'd like to be able to better detect lane markers in a variety of conditions. Right now, things are pretty ideal, but obviously when you're driving at night or in inclement weather or anything like that, the lane markers aren't quite as easy to see. So we'd like to be able to show that or complete this in a little bit more of a difficult circumstance. We'd also like to be able to detect lanes on curves and allow for lane changing, two things that we aren't able to do now. Curves, we could do it as shown in the original research, although lane changing she didn't do in her original research. I'm sure there's some way to do it, but we didn't do it for this project. And then the last thing we want to be able to do is highlight the lane from the vehicle perspective as the original research did, but we found it pretty difficult to translate that bird's eye view image back into the perspective of the driver. So
And
in
that's
conclusion,
a transform that is really fairly non-useful from a self-driving like algorithm perspective, but it's really just satisfying for the user to look at, particularly if they were a driver sitting in the car of an autonomous vehicle. That would be some peace of mind to be able to see how accurately it's tracking the lane from your perspective.
okay, so in conclusion, the video that we showed you guys hopefully shows how accurate things were able to get, at least in this ideal circumstance. We also showed that lane filtering can be done without color thresholding, which is a little bit of a step away from the original research. And then the last thing is unwarping the bird's eye image. It's a little bit more difficult than we thought it would be. There is some built-in MATLAB functions, but they didn't work the way we expected them to, and some other people had similar issues. So we weren't able to get that working the way we wanted it to. All right, thanks for watching.
Thank you.